Continuing our discussion on I/O subsystem, we will today talk of I/O operations. So far, we have seen the peripheral devices and the buses which interconnect them. Now, we will try to see how the whole thing works together. So, we will try to view the whole thing from a software point of view, as seen by a programmer how the entire activity appears. We will look at the issue of how I/O devices are addressed, and one crucial thing in I/O operation is checking the status or identifying when certain events are occurring. And finally, we will talk of a mechanism which allows memory and I/O devices to talk to each other. Initially, we will see from processor point of view, that is what I mean by saying talk from software point of view. So, we will see how processor participates in this activity, and finally, how memory directly interacts with the devices. So, as seen by the software, a high level language programmer tries to see the I/O activity in terms of some abstract statements. For example, you have statements like printf and scanf in C, and your view of I/O as a high level language programmer would be in terms of what these statements can do. Okay. So, you can you can send the data out, you can get the data in through these statements, and these are fairly high levels of abstraction. So, once you look at these at the low level, at the machine language level, there are lots of details which need to be taken care of. For example, you need to worry about the formatting of data. So, when you are using printf statement, you look at the data as high level language program sees it in terms of arrays and structures, and these structures could consist of various types of primitive elements, integers, floating point, strings, and so on. So, how all this has to be converted into raw form of data, that formatting has to be done. The values have to be encoded in the form in which devices can understand, and each device will have its own way of representing information. So, for example, a display device understands things in terms of matrix of pixels. A character level device such as a keyboard understands things in terms of ASCII characters, and so on. So, the information when it is coming in has to be brought in from the form which peripheral device is sending into a form which a programmer would like to see, and vice versa. Then the I/O operation at the low level have to deal with the interconnection structure between the device and the processor or memory. What kind of hardware is there, what kind of bus is there. So, how to get the data through these paths or the structure has to be seen, and then timing characteristics of the devices also has to be taken into account. For example, if you are trying to read from a particular disk track, it takes time to have the head move from that from the current position to that position. So, there are certain timings involved which have to be taken care of. So, all these details have to be taken care by the system software, and a programmer gets an abstract view. So, to be more precise, what is the role of system software in this whole operation? So, you have format conversion, for example. So, you have I/O library, which when you compile a program, there are a lot of library functions, library routines which get linked up into your object code. So, they take care of converting some of the abstract operations into low level operations. So, things like format conversion would be handled at that level. Then there are complex details of the device itself, the issue of dots or the pixels in the pixel matrix, or the question of tracks and sectors of a disk drive. These details are known to what is called device driver. So, device drivers look at specific peripheral devices or a family of peripheral devices and understand the details of how these work, how the information is to be handled, and so on. Then you require to work with interrupts. So, the events which occur in the I/O devices or their timings, they have to be handled through interrupts or exceptions. and as we have seen earlier that these are handled by exception routine or interrupt handling routines, which are part of OS kernel. So, there is an interrupt system, the number of interrupts which are possible for a given processor, and they are handled by a portion of OS kernel. Then there is also a question of multiple programs or multiple processes sharing different peripheral devices. So, several programs or processes trying to share a disk or share a printer or display. On display you have multiple windows coming up due to multiple tasks. So, the sharing also has to be looked after, and that is the role, one of the roles which OS plays. Then in devices like disks or hard disk drives, floppy disk drives, CD-ROMs and so on, the information is organized in terms of files. So, you have certain logical view of files as you see in a high level language program, but these files have to be mapped to physical devices in certain manner. Okay. So, you see some records in the file, at the physical level they may be tracks and sectors. So, how this mapping is done is taken care of by the file system part of the operating system. So, there are all these different aspects which take a lot of drudgery of IO operations away from a high level language programmer. Now, the requirement of different devices could vary quite vastly depending upon nature of the device, the kind of speed it has. There could be the demand which these devices place on the system may be quite different. If you consider for example, slow devices like keyboard or mouse, then these are producing information which is governed by the rate at which a human operator can enter. For example, keyboard is limited by the speed at which you would type. Okay. So, the demand is that you are transferring at times only one character, one byte at a time, or maybe a small group of bytes at a time, and the rate at which this happens could be just a few bytes per second. Same thing you could say about mouse. The mouse basically is tracking the position, and as you move the mouse from one place to other place, essentially what is being sensed is the movement, whether it is in plus x direction, minus x direction, plus y or minus y, or a combination of these. So, from one position to other position, the movement is slow. Imagine that processor is working at the rate of several gigahertz, okay, and the mouse movement is in terms of probably a fraction of second. So, the rate at which the information is being generated is pretty small. So, you are handling small volume at a time, maybe just a character or a few characters, and at a small rate. On the other hand, if you look at network as a peripheral, the rate could be fairly fast, and you also look at a block of information. You are not talking of sending a byte on a network or sending 10 bytes on network. It is always in terms of big blocks or packets. So, the way in abstract terms you like to see network operation is that you have a block of data in memory, okay. You want it to be sent out on the network, or you have a block of data coming from a network port, you want it to be placed in a particular position of memory. So, the rate could be for example, the network standards talk of 10 megabits per second or 100 megabits per second or 1 gigabits per second, now even going to 10 gigabits per second. So, which would mean typically a few hundreds of few tens or hundreds of megabytes per second. Okay. Now, let us turn our attention to graphic display. In graphic display, what you want is some picture or some text or some combination of these which is steadily displayed on the screen. So, that means the information on the screen has to be refreshed, so that a human eye sees it as a constant image. So, you need to refresh it several times a second. It could be 25 times a second or 30 times a second. And what is done is that you maintain an image of what you want on the screen in memory. Okay, so it would be called video memory, and this memory would be within the address space of the processor. So basically, any change you want to do on the screen, you modify a certain area in the memory, which is directly reflected on the screen. So there has to be some activity which takes a matrix of pixels as stored in the memory and refresh certain number of times per second on the screen. So this is how most of the modern systems work. In earlier days, the graphic display or the alphanumeric display used to be a peripheral separately, which was linked through a serial port typically. So it would mean that a sequence of characters or sequence of bytes would be sent reflecting what you want to display or the change which you want to make, and then some intelligence in the device would take that sequence of characters and modify the display accordingly. So there the rate at which you can change things would be limited by the rate at which you can encode the changed information and send it over a serial port. But now in PCs and all workstations, the information is directly picked up from a buffer in the memory and displayed. So you can continuously refresh from there. Look at disk drive. In the disk drive, typical operation you may like is that before you do the data transfer, you want the head, read write head, to be positioned on certain track and certain sector. So here is an operation which does not involve bulk of data transfer. It is a preparatory action which is required. So now looking at these 4 examples which I have taken, you can see large variety in terms of the rate at which data gets transferred, the quantum of data which is handled, and the mechanism of data transfer. For example, is data automatically being picked up from some area, or it is being explicitly transferred as and when required. Okay, so graphic display was an example where automatically the data keeps getting transferred, whereas in network or in mouse or keyboard example, we are doing it on demand. So as some keys get depressed on the keyboard, then the information gets transferred. Or in network, for example, when something comes from outside on the network, then a transfer occurs. In graphic display, you may change that pixel matrix as and when you want, but transfer from pixel matrix to the display device is a continuous activity. Now, for any of these operations, you need to address there are large number of devices. You need to talk to them, the processor needs to address them before it could talk to them. So each device, or strictly speaking the controller of the device, appears as a set of registers to the processor. Okay. You can view them as registers or view them as ports, in the sense that they are actually allowing you to talk to the outside world. So you can also call them ports. So what do you do with these ports? You can, for example, give commands to a peripheral device. So there would be some register in which command could be given. So you load some code in a particular register, it will be treated as command, and the device would be expected to work on that command. The command may also involve some parameters. For example, a command to seek the disk, you may have to specify the track number and sector number. You can read the status of the device. So basically, certain register would be designated as status register, and you can read that register and check specific bits to find out if certain things have occurred or not. Okay. For example, if key has been depressed on the keyboard, or a packet has come from the network or so on. Also there could be registers through which actual data could be read or written. So, all this each depending upon the requirement of the device, each device would be seen through a collection of registers, and these registers must have address, so that at any given time a program running in CPU can read or write a register. So, there are two ways addresses can be assigned to this. You can have a memory mapped I/O, which means that in the entire memory space, memory address space, you can leave some area which is earmarked for input output. So, you might say, for example, at the higher end of the address space, you are leaving 1K area which is not to be utilized for the memory, and it is dedicated for I/O. So, last 1000 addresses are reserved for register. So, or it could be first few, or whatever a particular architecture has in mind. So, you are basically reducing the memory space by a small amount, which may not really be very critical, and that area is available for I/O. The other alternative is have a separate address space for I/O. So, let us look at each of these. As I just mentioned, in memory mapped I/O, part of memory address space is reserved for I/O, and you can use the usual load and store instruction for reading or writing the register which are actually located in that space. So, memory is designed to ignore the addresses which are falling in that range. So, let us say you are using last 1K addresses for I/O in a given address space. So, if a load occurs, if a load instruction is executed and address is found to be falling within that range, the memory does not respond, but appropriate I/O device to whom the address has been assigned will respond. Okay. So, the data which will be sent to the CPU will not be by memory, but it will be the particular I/O register which will send the data. And similarly, when you are doing a store instruction, depending upon where the address falls in memory range or I/O range, the data will go to memory or I/O accordingly. In the second approach, you have to have a different address space for input output, and it need not be as large as what you have for memory. It is much smaller. It could be you could have let us say 10 to 15 bits trying to address the I/O devices. So, it need not be very large address space, and when processor is trying to read from memory or read from I/O device, the distinction would now be made by not by the address value, but by some control signals which will be flowing on the bus. So, in the first case, depending upon the address value, you can determine whether address is meant for I/O or for memory, but in this case same address could fall in both the spaces, and therefore, you need something additional to distinguish whether address is meant for I/O or memory. So, there are additional control lines which are included in the bus, and they indicate whether memory is being addressed or I/O is being addressed, and you need different instructions to work with I/O in such a case. So, there could be additional instructions similar to load and store, right, but different opcodes which will indicate that these are for transferring data to and from I/O devices. Before transferring data, a program would often need to check whether a device is ready for transferring data. Okay. So, for example, take the case of keyboard. The processor needs to determine if key has been depressed or not. So, it needs to periodically check whether key has been depressed and its code is available or not. So, this has to be done periodically, and the frequency at which you sample this has to be enough so that you do not miss out anything. Okay. So, if keys are being depressed at certain rate, let us say at the rate of 5 key per second, and you are checking only once in a second, then you are going to miss out. So, you have to check frequently enough, so that nothing is missed out. This approach is called polling, where you are periodically sampling and trying to see, you would read a status register, check particular bit and figure out if what you are looking for is there or not. An alternative is that processor does not get tied up in checking the status, it's busy with something else. Okay. It could be doing some other useful task, and whenever there is a need for device to invoke action from CPU, it will send an exception or interrupt. Okay. So, the device will intimate its readiness by raising an exception, and it basically means that a signal which is going as input to the processor is activated, and processor would have hardware which will transfer its control to exception routine whenever that signal gets activated. So, in general a processor may have multiple interrupt signals coming from outside devices. In terms of time, you can visualize the polling activity like this, that let us say some status is changing at this particular instant, and you are polling at certain rate. Okay. You polled here, spent some time in reading the status and figuring out if device is ready or not. You found it is not ready, do something else, come back, check it again, found it not ready, come back here, find that status is ready, then you carry out the transfer. Let us look at an example and put some numerical value, see what would be the implication of such an activity. Suppose there is a processor running at the rate of 500 megahertz or 500 megahertz clock is there, and every time you need to go and poll and take a decision, suppose it consumes 400 cycles. Then we want to see how much is the polling overhead for different types of devices with different speeds. So, let us say first example is mouse, which needs to be polled, let us say 30 times a second. Okay. And this figure is keeping in mind how fast one would typically move the mouse. Second case is you have a floppy disk drive which transfers the data at the rate of 50 kilobytes per second, and each time, every time you get 16 bits of data or 2 bytes. Okay. Then thirdly, you have hard disk drive which transfer data at 4 megabytes per second, and the unit of data which comes out is 4 words at a time, right. So, now in these three cases there is a vast variation in terms of speed, and your polling has to be faster and faster accordingly. As we will see that when you have to poll very frequently, you are wasting a lot of time, and CPU gets tied up to a significant extent in this polling activity. So, in the first case we are trying to poll at the rate of 30 times a second, so, and every time we poll we are wasting, we are let me not say wasting, we are consuming 400 cycles. So, 30 times 400 is the number of cycles consumed in polling every second, right, and CPU is running let us say 500 cycles in 1 microsecond or 500 million cycles per second. So, as a fraction or as a percentage, what is the fraction of the cycles which actually are lost in this activity and not in executing other computational instructions. So, we divide this, this is the number of cycles per second divided by this cycles per second, we get a ratio, convert that to percentage, you get 0.002%. So, it is a very small fraction of the time which is spent, and we will certainly not mind doing polling of mouse in this particular manner. Okay. Very little overhead. as we go to floppy disk drive, the rate of sampling or rate of polling is higher. So, we have to poll at least at this rate. Okay. Every data we should every data is coming at this rate, okay, 16 bits at a time. So, basically we are getting 2 bytes at a time. So, number of times we are actually transferring is 50 divided by 2 into 10 to the power 3. So, this is 50 kilo bytes per second, taken half of it because divided by 2 bytes at a time. So, we must poll at least these many times per second, all right. And again similar factors, 400 cycles lost every time you poll, divide by the processor clock, we have 2%. That means, only 2% of the cycles are dedicated for this. So, this is not as comfortable as mouse, but still tolerable. The only problem is if we had several of such devices, then these percentage would add up and we would have lost sufficient time. But with the, let us say this in isolation, it is still a tolerable device if you do not have too much of other activity. Finally, we move to a even faster device, 4 megabytes per second and 4 words at a time. So, this 4 megabyte per second figure is divided by 16 because we are trying to transfer 4 words or 16 bytes at a time, and each time we transfer we spend 400 cycles, divide this by the clock rate, we get a figure of 20%, which is clearly undesirable. You cannot spend 20% of the time just polling a particular device, right. So, we need to do something better than that, and solution for that is interrupt driven input output. Here what we do is we allow a device to inform the processor as about its readiness. So, processor will probably instruct the device and ask it to send an interrupt or send an exception as and when it needs processor attention. So, processor attention is given to the device by transferring control to exception handling routine, and exception handling routine would do the needful. So, the way you handle exceptions here coming from external world of input output, the mechanism is same as what you do for internal exceptions which may come because of arithmetic overflow or illegal instruction or page fault and so on. The difference here is that these exceptions which are coming from outside, they are asynchronous with respect to the instruction, whereas internal exceptions will come at specific time. For example, arithmetic overflow would be detected in a specific cycle of an instruction, but exception or interrupt from IO device could come in any cycle. Okay. It has no link with a specific instruction, and therefore, what you would typically do is that at the end of instruction execution, you will see if there is an exception from external world and then respond to that. These exceptions are given comparatively lower priority as compared to internal exceptions. Among these external exceptions, the priority may be according to the speed. So, devices which are faster need early attention, and therefore, they are given priority. Slower devices are given lower priority. So, you might have several exceptions occurring from IO devices at the same time, and you will serve them according to the priority. Similar to internal exceptions which we discussed earlier, the mechanism could be vectored interrupt or non-vectored interrupt. Vector interrupt means that the control directly gets transferred to an exception handler which is meant for a specific exception, and in non-vectored case you set the cause of exception in a particular register, but transfer of control takes place to a specific location, and then you are going to run some code, check that cause register and branch off to one of the points. So, both the possibilities exist here also. Now, let us get back to a similar scenario and try to quantify the overheads of interrupt driven transfer. So, we have same processor working at 500 megahertz. Now, let us say that overhead per interrupt is little more than the overhead of polling. So, suppose it is 500 cycles, and we want to see how it is going to work in case of hard disk drive. Now, if disk drive was always active, then things are going to be as bad as polling. Okay. So, you will get continuous interrupt. In fact, it would be worse because every time there is an interrupt, the overhead is larger. But the reality is that device or hard disk drive in this particular case will not necessarily be always active. So, suppose it is active in entire duration of program execution only 5% of the time. Okay. So, when it is busy, then data is coming at a fast rate. When it is not busy, there is no activity. So, in such a case, we will definitely have saving of time here, because the device would inform only when it needs the attention. When it is inactive, nothing will happen and there are no interrupts. But in a polling based approach, you have to continuously keep polling. Okay. So, now we have the overhead if the device was continuously busy. We have same expression 4 megabytes per second, 1 by 16 because we are transferring 16 bytes at a time. This is the overhead number of cycles per interrupt, and divide by the clock frequency, we get 25%. So, instead of 20% we have 25%, but since we assuming the device is only busy or active 5% of the time, we take 5% of this and the real overhead will be 1.25%. Okay. So, that is where it will score. Now, at times even 1.25% overhead may also not be desirable, particularly when you have number of such devices. Hard disk drive in a system is only one, you have display, you have network, and you have other things. So, if all such overheads are added, then lot of process time will get consumed. So, a solution for that is not to involve processor in transfer of every word or every group of words. What you could do is you could allow the device to deposit data directly into the memory or read data directly from the memory, and that operation is called direct memory access. So, the processor's role in direct memory access would be only to initiate the transfer or set up things, to tell the device that this is the amount of data you need to get. Let us say if it is disk, that from track number so and so, sec number so and so, get so much of data, and it also specifies that this data has to go to this particular area in the memory. So, once that initialization is done, the processor can get busy with something else, and as the words or bytes come from disk drive, they get transferred directly to the memory, and processor does not come to know of that. The processor of course needs to be informed when the entire job is done, and that time processor can see, check whether the transfer has taken place correctly or not. For example, if in between you found a bad sector or something, some error occurred, then status would be set accordingly and processor interrupted. So, the processor has to see at the end whether the IO operation ended successfully or there was an error. This entire job actually is entrusted to a special controller, which is a special piece of hardware, it is called DMA controller. So, it is in the DMA controller you would specify memory addresses, amount of word, amount of data to be transferred, the direction of transfer, and what is to be done at the end of the transfer. A DMA controller could actually take care of not just one peripheral device, but multiple peripheral devices which are required to transfer data directly to the memory. So, it could be a 2-channel DMA or 4-channel DMA. 4-channel DMA for example, would allow 4 high speed devices to transfer data to memory or read data from memory. Okay. So basically it's you could say it's an extension of the processor logic or augmentation of the processor logic, which looks after this. So the sequential addresses in the memory will be provided by this DMA controller. It will start from the starting address, and as and when data comes, it will keep on updating the memory addresses and detect when the whole transfer is done. Now, let us try to quantify the overheads in a DMA like situation. So, we again have same processor running at 500 megahertz. Suppose initiation of DMA requires 1000 cycles. So, everything initially is set up, and that is one time when processor gets involved. Next, the processor gets involved when end of DMA interrupt comes, and let us say 500 cycles get consumed in that. So, in one DMA activity, basically the CPU is spending 1000 cycle plus 500 cycle. Let us imagine that the block size or the chunk of data which gets transferred in one DMA is 8 kilobytes. So, by spending these 1500 cycles, the processor will achieve transfer of 8 kilobytes, and for next 8 kilobytes you may have to repeat the process. So, we can now even look at situation when hard disk drive of the kind we discussed in previous example is always active. So, suppose it needs to transfer 4 megabytes per second continuously, all right, and the overhead then will be, you have 4 megabytes per second transfer rate, and since each time each DMA operation requires 8 kilobytes, the ratio of these two will give how many DMAs per second are being done. Okay. And each time you do DMA, you are spending these many cycles, this in the beginning, this in the end, and divided by the clock frequency will give you the fraction of time spent on the DMA by the processor. So, of course, DMA controller has to do lot of work. The work has been taken off or outsourced by the processor here. So, this comes out to be okay. You can see that the first factor, the ratio of these two is 500. This is 3 into 10 to the power minus 6. So, it comes out to be 0.15%, which is quite an acceptable figure, all right. So, as we have seen from polled transfer to interrupt transfer to DMA transfer, depending upon requirement of the device, we can choose a suitable mechanism for transfer, and as you go along this progression, there is higher and higher performance, but there is a cost issue also. DMA controller means additional cost. Similarly, interrupt also requires certain mechanism. So, there is extra hardware which also adds to the cost. One step further from DMA is the concept of IO processor. A DMA can be initialized to do one block transfer, but an IO processor could actually be asked to do a sequence of many DMA like operations. So, it could be asked to do, let us say, read a block from the disk, that is operation number 1, send a block of a different size from a different area in the memory to the network controller, that could be second operation. Third could be send a block of data to printer and so on. So, a sequence of operations, each typically involving a DMA of certain block size could be defined, and IO processor could go through this sequence. So, for an IO processor, each appears like an instruction or an IO operation. Okay. So, these instructions could be stored as a small IO program somewhere, either in a dedicated memory for the IO processor or somewhere in the main memory. So, each IO operation is a major activity, and IO processor will sequence from one to other in this particular manner. Now, when we are talking of DMA, essentially there is a direct communication between memory and one or more I/O devices. Now, how do you view this in light of the fact that memory is not something flat, there is a memory hierarchy. You could have cache, one or more levels, and you also have virtual memory. So, how does this whole thing work when memory hierarchy is present? So, what are the problems caused by presence of virtual memory? The programs which are running in the processor, they look upon memory in terms of virtual addresses, okay, whereas the DMA devices will typically work with physical addresses. So, there is a discrepancy between these. What it may mean is that you would need to do translation of the address. So, when you are initiating a DMA, okay, you would need to specify a physical address for the DMA controller. So, you need to tell DMA controller that transfer, let us say 8K bytes of data to this physical address, and the program would be working in terms of virtual addresses. So, if you have created an array, you know its virtual address. So, there has to be an explicit conversion of that virtual address to get to the physical address. Now, remember that the virtual addresses do not map linearly to the physical address. Okay. So, in virtual address you have, let us say, one page and then next page contiguous, but they may map to two pages in the memory which are not contiguous, which may be at arbitrary addresses. So, it may not be sufficient for this translation to be done once. One of the ways to handle this is that you restrict each DMA activity to at most a page. Okay. So, suppose your page size is 4 kilobytes and you want to transfer 8 kilobytes, then there is a problem that for your data is coming in 2 pages, you need to specify the physical address for each page. Okay. You can't specify one physical address and say that transfer 8 kilobytes of data to this, because it may not go to contiguous areas in the physical pages. You want them in contiguous area and virtual space, but in physical space it is not contiguous. If you limit your data size or DMS data size to one page, then this problem is taken care of. Okay. So, basically if you want to transfer larger piece of data, you have to break it up and incur the overhead of multiple DMAs. What about cache? When you have cache, what problems it can possibly bring in? There is essentially a problem of consistency, because CPU is directly talking to cache and not to the memory, okay, whereas a DMA device will typically have no access to the cache. It can write to the main memory or read from main memory. So, there is a problem of consistency. One of the two memories may have more recent information as compared to the other. So, for example, if there is a DMA input happening, the information coming from device is getting put in the memory, and suppose it gets put in the block for which copy exists in the cache, then what you have in the cache is out of date. The information in the main memory has been updated by the device, and what you are seeing in the cache, what processor is seeing in the cache is stale information. It is not up to date. You can also have reverse happening, that CPU has put something in a cache block and it is expected to be sent out to a device through DMA, but a DMA controller will pick up information from memory which is not yet updated, particularly with write back cache, where there is a where you are not updating main memory immediately. So, in write back cache, if you recall, data in the memory gets updated only when a block is getting evicted. So, you keep on making updates into cache blocks, but if corresponding block from main memory was being written to a DMA device, then you have a problem. So, this actually similar problem occurs in multiprocessor cases also. Imagine that you have multiple processors which are trying to share same memory. They would typically have their own caches. Okay, so, just imagine two processors, they own cache, but a common shared memory. So, once again, if there is a data which processor 1 has to communicate to processor 2 through shared memory, the two caches may be inconsistent. So, the solution for this lies in actually what is called cache coherence protocol. So,
limit the data size to a page, won't it limit the overheads?
You are talking of the first problem, virtual memory. Yeah, if you are limiting your data size to a page for DMA transfer, then you are definitely increasing the overhead. So, suppose you were to transfer 16K bytes of data in DMA, and your page size is 4 kilobytes. If this virtual memory problem did not exist, you could have incurred the DMA overhead only once, but now you will have to break it up into 4 DMAs. Each time you supply appropriate physical address, and DMA occurs without any problem, but the overhead is occurred 4 times. So, you are increasing the overhead. Okay. The problem of cache incoherence is solved by what is called cache coherence protocol. So, these protocols are additional actions which cache controllers have to take when multiple copies of data exist in multiple caches and memory. So, there could be one or more cache in memory, which is cause of having multiple copies of data, and something is getting updated, something is not getting updated, which is the problem of coherence. So, these protocols, I will not go into details of this, are designed so that coherence is maintained, or at least if two copies are going out of sync, everyone comes to know that they are out of sync, and one waits till updation occurs. So, this also means additional overhead, additional work which has to be done. Okay, so I will stop at this point and summarize. We started by looking at the role of system software in IO operations, and we noticed that the software is required. System software particularly has to handle device specific details, it has to handle interrupts, it has to take care of sharing of device by multiple processors, look at the file organization, and so on. We saw that devices are viewed as set of registers by the processor, and they can be addressed either by using part of the memory address space or defining separate address space. We saw two mechanisms of checking the device status, polling and interrupts. Polling has higher overhead, particularly it becomes undesirable for fast devices, and interrupts is used. And then there are times when interrupts are also not acceptable. You have to have direct communication between memory and the device, that is called direct memory access. So, which is a complex mechanism, but it is essential for fast devices like network controller, disk drive, and so on. I will stop at that. Thank you.